Alright, so we are looking at a sample distribution for means now. So, looking at this information up here, we know that this has a mean of 16 with a standard deviation of 5. Okay? So, we're going to do a sample of 5 people. Okay? N equals 5. And there we go. So we took a sample of 5 people and it plotted the mean for those 5 people. Okay? And we're going to do it again. And then we're going to do it again. Okay, and these are all the means of the 5 people that we sampled. So now let's do 10,000 samples of 5 people. Well, what do we notice? Well, the first thing that we notice is that the center here is approximately the center here. As a matter of fact, the mean of our sample is 15.96 and the mean of our population is 16. So this is a pretty good approximation of what the mean is there. Well, the other thing that you might notice is that you might say this looks like it's unimodal and symmetric, and this is also unimodal and symmetric. However, the population has more variation than our sample does. And you're absolutely right. Okay? And the reason is that when we take 5 people out, and let's say we just do 5 people, and we plot the mean, we put it into this distribution. Okay, what happens is when we're plotting those means, then what happens is our variation will decrease. Okay. All right, so let's say that instead of plotting 5 people at a time, we're going to do 10. So we're going to double our sample size. So here we go. We're going to take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people and plot the mean. Okay, and then we're going to do it again. Okay, there's another 10 people and we plotted the mean, and then, okay, there's another 10 people, plot the mean. Well, let's do it 10,000 times. Well, guess what happened? We got a distribution that is centered and about the same spot. Okay, don't come in Monday morning and tell me I don't know how to draw a straight line. I'm doing this freehand on a program I have, so I understand that it may not be perfectly straight, but you get the idea. It's centered at the same spot. Okay, the mean here is 16. The mean of our sample distribution is approximately 16. Okay. But what happened? What else happened? Well, you'd say the shape is the same, though it has less variation. But it also has, and compared to our distribution with samples of 5, it has less variation. So when we take larger samples, and the same thing happened with proportions, if you remember, when we took larger samples, the variation decreased. Okay, and the reason is that when you are taking larger samples, those people that tend to be sort of outliers get eaten up in the average when you're taking a larger number of samples, as opposed to when you take samples of only 5 and you get somebody who's kind of an outlier. That person affects the mean more than when you take a sample of 10 and you have kind of that outlier person. That person doesn't affect the mean as much, so they don't get to affect the variation as much. Okay, so here, let's see if we fit a normal model. That fits pretty good. Okay, so nothing surprising there, right? Okay, so let's change the population distribution, this guy up here. We're going to go to a skew distribution. Okay, So let's say this is a dummy class, okay? You know, we gave a test and everybody scored in the lower end and a few people did well. Okay. So let's say now that we're going to do, I'm going to just start out doing samples of 2 people and plotting the mean. So here's what's happening. 2 people plot the mean. 2 people plot the mean. 2 people plot the mean. I'm going to do this a few times. Okay, so you get the idea. Okay, so let's do 10,000 people. You say, okay, let's talk about what happened in comparison to the population distribution. Well, what happened is we had a mean up here of 8.08, and our sample distribution down here has a mean of 8.03. So our mean in our sample distribution is a pretty good approximation of what the mean is from the population distribution. Okay. Now the shape of this is clearly skewed right, and the shape of this is skewed right also, but less so. Okay, I wouldn't call that roughly unimodal and symmetric. It's clearly skewed right. Okay. All right, so let's go to samples of 5. All right, so there it is. Okay, we took 5 people, plotted the mean, another 5, plotted the mean, another 5, plotted the mean, another 5, plotted the mean. Okay, and then let's do our 10,000. Okay, so let's see what's happening now. Well, in our distribution, our population distribution, our mean is 8.08, and our sample distribution is a mean of 8.05. Pretty good approximation. Okay. Now, the shape of this is clearly skewed right in our population distribution. What about in our sample distribution? We can argue down here if we were to fit a normal model. You say, nah, that doesn't fit, but that's pretty close. Okay. We can argue that that is roughly unimodal and symmetric. Okay, though there's a slight skew to the right. Okay, but that's still a pretty small sample size, right? All right, so let's kick it up. Let's go to 16 people. Okay, so we're gonna take 16 people from our population, and we're gonna plot the mean of those 16 people. We'll do it one more time, and let's do 10,000 samples. Okay. So, now what happened? Well, no surprise, the mean is a good approximation of the mean of the population. Okay. However, though our population distribution up here is skewed right, our sample distribution is pretty much unimodal and symmetric. If I fit a normal model to it, it's pretty close. Okay. Well, that's pretty powerful for us, because if you remember back to when we were talking about normal models in chapter 6, I believe it was, you know, what's the condition to use a normal model? Well, you got to have a distribution that's unimodal and symmetric. You can't use a normal model on this distribution, but we can use a normal model on this distribution. Well, you say, Mr. O'Neill, if I know that the population distribution is skewed, I wouldn't use a normal model. Well, here's the point. When you do samples, you may not know that it's skewed. Okay, a lot of times when you're doing sampling, you don't know what that distribution looks like that you're drawing your sample from. But what happened is, when we drew larger samples, when we took small samples, when we did sample sizes of 2 and sample sizes of 5, we run the risk of winding up with a skewed distribution. Okay? But when our sample sizes are large enough, even though our population distribution is clearly skewed, our sample distribution comes out to be roughly unimodal and symmetric. Hence, we can use all those things we know how to use from normal models, because it meets the condition. Okay? So that's going to be a powerful thing for us moving forward, in that, don't forget, this up here, guys, is many times not known and not even knowable. Okay? If I was to, let's say the average height of a senior in the United States, a female. Well, I can't measure every female in the United States. It's impossible. Okay, I may not know what this distribution looks like. Okay, it could be skewed. I wouldn't expect it to be, but it could be skewed. Okay, but as long as my sample size is large enough, it doesn't matter if it's skewed, because my sample distribution is going to cancel all that out. I could take any distribution I want. I'm gonna do this guy right here. I'm gonna do something. I'm gonna do bimodal. Okay, bimodal distribution. Okay, if I take small samples, okay, let's do 10,000 small samples. I get that. Okay, but that's only taking sample sizes of 2. Okay, so you could say, well, that looks kind of trimodal. Okay, although if we were trying to fit a normal model to it, it doesn't fit real well. Okay, but let's take sample sizes of 20. 10,000 sample sizes of 20 from that distribution right there. Bingo, look at that. Roughly unimodal and symmetric. Doesn't matter. Okay, so it doesn't matter what that population distribution looks like, as long as we take samples that are large enough. We're going to get a sample distribution that is roughly unimodal and symmetric. That's the whole premise of the central limit theorem. Okay, that's what this is all about. This is called the, we're going to be looking at the central limit theorem, and that's basically what it is. It's that it doesn't matter what our population distribution looks like or what it does, as long as we take samples that are large enough, our sample distribution is going to be roughly unimodal and symmetric, and hence we can now use all the tools we know how to use from our study of normal models, and we can proceed going forward with using those tools. Okay, so we'll look at knocking this out in the notes in the next section. Okay, so the mean of we're talking right now about the CLT, which is called the central limit theorem. And we looked at in the last applet, basically the premise of the central limit theorem is it doesn't matter what our population distribution looks like. Our population distribution could be symmetric, our population distribution can be skewed, our population distribution can be bimodal, something that looks like that. Okay, as long as our sample size is large enough, we're going to get a sample distribution. All these have a mean, right? We'll call the mean mu. And what mu is the mean of the population. Okay, we're going to get a sample distribution as long as our n size is large enough. It's going to have less variation, but it's going to have a mean where x bar is approximately equal to mu, and this sample distribution is going to be unimodal and symmetric. And what that's going to do is that's going to allow us to use a normal model. And all that's based on this. The sample is large enough. The sample is large enough. Well, you might be asking me, well, what's a guideline for large enough? Well, what's generally considered large enough is 40. If your sample size is 40 or more, then it's generally this distribution in the population can be as
as whacked out as you can think, okay, but it doesn't matter because the sample distribution will come out to be unimodal and symmetric. Now that doesn't mean that if n is less than 40 that this won't happen. Okay, if your population distribution is symmetric, then your sample distribution is going to be symmetric. Okay, you can have a sample size of 4 and this is going to wind up being symmetric. It'll just have less variation because you're plotting the means. But when you have these other distributions skewed or bimodal, then a larger sample is going to be required to make your sample distribution come out to be symmetric so that you could use the normal model. Okay. So the mean of a random sample has a sampling distribution whose shape can be approximated by a normal model as long as the sample is large enough. The larger the sample, the better the approximation will be. The shape of a sampling distribution of any mean becomes more symmetric as sample size increases because you're plotting the means. Okay, when you plot the means, okay, the larger your n size, the larger your samples, okay, then the less variation your means are going to have when you plot them. The less variation that they have, then they come out to be nice and symmetric. And it doesn't matter the shape of the population distribution. Okay, it doesn't matter what that population distribution up here looks like. As long as n is large enough, our sample distribution is going to come out to be unimodal and symmetric. The mean of the sample distribution is x bar, which is an approximation of mu. Mu is from the population. Okay, mu oftentimes is unknown, and most of the time is unknowable. Okay. What's the average IQ of every adult that lives in the United States? I don't know. You're gonna have to sit down and give every person in the United States an IQ test. Is that feasible? Well, no, it's not. However, if we give a sample, we take a sample of people, and we use the concepts that we learned in chapter 12, where we make sure that our sample is representative, so we have some kind of randomization in selecting people, okay, then we should get a pretty good approximation of what the average IQ is. Okay, so x bar is our sample mean. Okay, that's this guy right here. Now the standard deviation is sample distribution, which we're going to call S, equals sigma divided by the square root of n. Okay, so what is S? S is your sample standard deviation. Actually, I'm going to put down sample distribution. Okay. It's the standard deviation of the sample distribution. So what's sigma? Sigma is the population standard deviation. Okay. Again, sigma is most of the time unknown and unknowable. Well, if you can't find mu, okay, because that's unknown and unknowable, then sigma, since standard deviation is calculated from the mean, that's going to be unknown and unknowable also. So when we're dealing with our sample distributions, we're going to be dealing with x bar, and we're going to be dealing with the sample distribution standard deviation. Okay, so how do we get that? That S equals the population standard deviation divided by the square root of n. And I'm not going to derive where that comes from. That's just a formula that that you're going to have to know how to use. It's on your AP formula sheet, so you don't have to memorize it, but that is a formula that we're going to use going forward. Okay? Alright, so in example 1 we have a, suppose the mean weight of an adult is 175 pounds, and I already marked that. That mean weight is mu, okay? With a sigma, or the standard deviation, of 25 pounds. An elevator has a weight limit of 200 pounds and a limit of 10 persons. So assuming a full elevator, calculate the mean and standard deviation of the sample distribution. Okay, so what would we expect this to look like? Well, if we took a sample of 10 people, okay, and plotted the mean, what would we expect the mean of that 10 people to be? Well, we would expect that mean of the 10 people to be around 175 pounds. So we expect X bar to be around or approximately 175 pounds. Okay. Now, what do we expect the sample distribution standard deviation to be? Now, again, what we're going to do is we're going to find the mean of these 10 people. So here's what the population distribution looks like. Here's the population distribution. It has a mean of 175 and a standard deviation of 25. So this would be 200, this would be 225, and this would be 250, and then this would be 150, 125, and 100. Okay? Now we're going to take a sample of 10 people from this distribution, and then we're going to plot the mean. Okay, so what would our sample distribution look like? Well, assuming that this is going to be roughly unimodal and symmetric to begin with, which we would expect weights to probably be fairly symmetric. It's a chance it could be bimodal, because you would have a hump for males and then another one for females. You might have two different averages there. But what we would wind up with is we would wind up with a sample distribution that would be centered around 175. And then what would our sample standard deviation be? Well, it would be 25 divided by the square root of 10. Okay. And then if we do that out, we get 7.9. So I'm going to round this. It comes out to 7.9, but for the sake of putting our distribution there, I'm going to make this approximately 8. So our sample distribution would go 183, 191, 200, and then 166, 157, and 148. Okay. So what's going to happen is this is going to have considerably less variation, because again, we're plotting means of 10 people. Okay, so I kind of answered what this second question would look like, and that is that that's what this would look like. Now on the AP exam, if you were doing this on the AP exam, don't round it to 8. I rounded it to 8 to make it easier numbers to work with. You would actually use the 7.9. The actual sample standard deviation is 7.9. Okay. And that says what's the probability that 10 people who get in the elevator will overload it. Okay, well, what would happen is we would need an average of over 200 pounds, because 10 people who get in the elevator can only hold 2,000 pounds. So if we divide 2,000 by 10, then the average would have to be over 200 pounds. So basically, we would have this. This is again now our sample distribution. We would have a mean of 175. That's X bar, and then we would have to have a mean weight of over 200. Now, we can just look at this and we know that's already 3 standard deviations to the right, so that's highly unlikely that's going to happen. But we just go to our normal model, and our lower bound is going to be 200 to, we'll just go up to some number up above 200. Our mu is 175 and our standard deviation is 7.9. Now you might be saying, well, Mr. O'Neill, this uses mu and sigma. You're right, it does. However, in our distribution we have X bar and S. So this will still work even though this is using what we consider to be parameters, when in fact we're using what we consider to be statistics. Mu and sigma are what we call parameters, and X bar and S are statistics. But that's what we have to work with, so we're going to put the 175 in for mu, and we're going to put that 7.9 in for our standard deviation, and this is going to come out right 7.766 e to the negative fourth. Don't miss that e to the negative fourth. That means you had to move the decimal 4 places to the left. So the probability that that happens is 0.0007766. So that is less than 1%, and that is highly unlikely that that's going to happen.